The right triangle bounded by the x and y axes and the line of 3x minus y equals 6 contains 2 lattice points in its interior. How many lattice points will be contained in the interior of the triangle bounded by the x and y axes and the line 3x minus y equals 24? So this is a great example of Pick's theorem. So Pick's theorem states that in a lattice polygon whose boundary consists of a sequence of connected non-intersecting segments, the area is I plus b over 2 minus 1, where I is the number of interior lattice points. In this diagram, it's the green dots, and b is the number of boundary points. Note that this is also included. And then, yeah, you get the area based on this. Proving Pick's theorem is is quite tricky. The idea is to build it up. So you can prove Pick's theorem on right triangles fairly easily. And then at which point you can put together right triangles to form any polygon. For example, here you can divide it like this or something. Voila, you've divided it into right triangles. And then because each boundary point, when you combine two things, it's counted half on each side, and then it becomes an interior point and it gets counted 1. So everything is preserved. So technically I could work through, I could just go through the motions of the proof of Pick's theorem for a right triangle in this problem, but I'm just going to apply Pick's theorem because it's easier. Okay. So the figure we're working with is this little triangle here, and we're trying to find the number of interior points. So firstly, we know what the area is. The area is equal to, since this is a right triangle, 8 times 24 over 2, which is 96. Number of boundary points, there's going to be 8 of them here. Okay, so there's 9 on this side because 0 through 8, 0, 0, 1, 0, blah, blah, up to 8, 0. Along this side, there will be 25 because 0, 0, 0, 0, and 0, negative 1, all the way to 0, negative 24. And along here, there will also be 9 of them because there will be 0, negative 24, 1, negative 21, 2, negative 18, 3, negative 15, 4, negative 12, etc. Basically, as long as x is an integer, then y is an integer. So there's 9 of them, but we've overcounted here the vertices. So in total, there are 25 plus 9 minus 3, which equals 40. So b equals 40. And in this equation here, we know the area, we know b, and the only variable left is I, the number of interior lattice points. So we can just plug numbers in. So 96 equals I plus 40 over 2 minus 1. And rearranging, this becomes 77. Yeah,